Hi guys, Professor Stevens here. I'm going to work through this problem which was requested by a student. It's a great problem to work on. It's very commonly a source of frustration for students because when you look at a problem like this where we're solving a rational inequality where you have a fraction involving a variable in the denominator, our very first instinct usually is to clear the fractions, which is actually the incorrect way to deal with this type of problem. Even though in many other problems that is the recommended first step, here we want to not do that. So the first thing I want to point out is that when solving a rational inequality, do not clear the fractions. Instead, you want to set the inequality to 0, moving all the terms over to one side, and then combine them into a single fraction. Then once you do that, you'll divide up the number line into regions because our answer, since we have an inequality rather than an equation, when you have an equal sign there, there's usually just a couple of answers that you can put into your solution set. But with an inequality that involves less than or equal, any of the symbols like this, this, all of those involve interval answers, not just a couple of listed solutions, but entire regions of the number line. So because of that, we will be having to split up our number line into regions and then do some testing to see which regions make our original inequality true. All right, so that was a mouthful. Let me just repeat. One, we set it to 0 combined to a single fraction. Then we will divide the number line into test regions by finding values of x which make the numerator and the denominator equal to 0. That will be what we call critical values that divide up our number line into regions. Once we have those critical values, we will determine which regions make the original inequality true by testing values from each region to see how they work when you plug them in. All right, so let's get started on the first step here. I'm just going to take my inequality. I'm going to use black for this. 12 over x plus 6. And I want to subtract 2 from each side so that, like I said, I have everything on one side and the other side is just 0. So that's what we mean by set to 0. Then also we want to combine into a single fraction. So to do that, we will have a common denominator. I'm going to rate my 2 as a fraction. Negative 2 over 1 is the same thing as negative 2. And then I will multiply on top and bottom by the common denominator, x plus 6, because when I multiply anything over itself, that's the same thing as multiplying by 1. So multiplying just the left side by x plus 6 over x plus 6 is like I've just multiplied the entire left side by 1. It doesn't change the quality at all. It doesn't set things off balance. It is just the same quantity, but it has a different look to it so that I can combine into a single fraction. So this is an equivalent inequality when I write okay, so that whole line here that I just wrote is equivalent to the original inequality. And that's a plus sign. I know it looks a little sloppy. Let me rewrite that. Notice that I took that negative right here that was originally out in front of the 2, and I just made sure to put it as part of the numerator, and that's going to help me with simplifying the next step. And so I'm going to simplify by distributing the negative 2 into my quantity x plus 6, and I will also combine into a single fraction. So now that I've got a common denominator here on each of my terms, my resulting equation in the next step, or not equation, but my resulting inequality in the next step, will have that common denominator of x plus 6 I'll have the 12 from the first term, and then I'm just going to distribute so that I have negative 2x minus 12. And the 12 and the minus 12 cancel each other out. So finally, I have this equivalent inequality like that. So that completes step number 1. Step number 1, set to 0 and combine terms to a single fraction. We've done that now. Single fraction on one side, 0 on the other side. Step 2 is to take that result and use it to find critical values. All right, so now that I've got my single fraction, I'm going to start using that to find critical values. So I'm going to set my numerator this way. The numerator is 0 when, okay, how do we figure this out? When is the numerator going to be 0? I'm going to take my numerator, negative 2x equals 0, and solve for x. That 0 is negative 2 divided by negative 2 is just positive 1. 1 times x is just x. So I get x equals 0 divided by negative 2, which is 0. So that is one critical value. And then I will find another critical value using my denominator. Okay, so the denominator is 0 when x plus 6, right? So looking at the inequality here, x plus 6, x plus 6 equals 0 when x equals negative 6. So that's my second critical value. Right, so my two critical values will now be used to split up my number line. Okay, so here's my number line, and this is for x values that would make my inequality true. I'm trying to figure it out, and I'm using my critical values here, x equals 0 and x equals negative 6, to split that up. So let's say this is negative 6 and say this is 0. I'm actually splitting up into regions with those as dividing lines. And then I'm going to pick test values in each region to determine which would be part of my solution set. So I've just divided up my number line from negative infinity to negative 6. And something that's important to note here is that I'm going to use a soft parenthesis there. And the reason I'm doing that is because my original inequality has x plus 6 in the denominator. So x cannot be ever allowed to be negative 6 in my final solution set, because if it were allowed to be negative 6, that would make my inequality undefined. So it's always a good idea when you first start a problem like this and you're looking for your solution set, if you think of it, it's a good idea to start off with making a little note to yourself about what to not include in your final solution set. So just putting a note, this has to be considered when you're finalizing your answer. And so, you know, you can make a big open circle here to help you remember that. I'm using a soft bracket, and I'll do the same thing over here from negative 6 to 0. Now 0 would not make my inequality undefined anywhere, so I can use a square bracket for that. And from 0 to infinity. So those are the three regions that I need to test from here in order to determine my solution set. So I'm just going to make a copy of it for the next slide. And we're going to go on now in narrowing down the options by testing each region of the number line. So now I have to select test values. I'm going to select in this region -7, in this region -1, and in this region +1. I'm just selecting values that I think are going to make the arithmetic the easiest to do in each region. Alright, so I'll start with, let's test what happens when x equals -7. So using my original inequality, I'm just leaving space for the x value. I'm looking to see if when I plug in -7, if my inequality is true. So, whoops, simplifying this, I get 12 over -1, which is -12, and that is less than or equal to 2. So because that is true, then I will use that region. This part, this section is going to be part of my solution set. Okay, and we can go ahead now and test the next one over. So we've already tested this one and it worked out well. We're going to test the next value, x equals -1. So now, testing x equals -1. Again, starting with that original expression or inequality, plugging in for -1, and simplifying, I have 12 over 5, which is actually not less than or equal to 2. 5 goes into 12 more than 2 times. So this inequality is false when I use x equals -1. So no good here, right? So I will not be using this region as part of my solution set. And then one more to go, x equals 1, so we'll go ahead and test that. Okay, so I have 12 over x plus 6 less than or equal to 2, and I'm plugging in a +1, and then I get 12 divided by 7 is less than or equal to 2. This is true. Back at my regions up here that I've already mapped out, I'm going to have it from -infinity to -6. Union, and then including 0 up to +infinity. So right here, square bracket, and that square bracket has is being used because of the equality in the symbol in my original inequality. It has less than or equal to, so you can include x equals 0. Remember, we're not including -6 because it would make the denominator 0. So that's the final answer right there. Solution set from -infinity to -6, union from 0 inclusive to +infinity.